Welcome to the debate. When you picture like a pristine ballerina, you don't exactly picture them wearing lead boots, right?
No, definitely not.
Right, because agility inherently relies on lightness. But, well, in automotive engineering, we are about to see if code can actually make lead dance. In 2027, BMW is launching the first fully electric M3.
Codename ZA0, right?
Exactly, the ZA0. And it packs a massive 100-plus kilowatt-hour battery, which really begs the central question for us today. Can a high-performance EV maintain the legendary agility and track longevity of an M3 despite hauling all that massive battery weight?
It is the defining engineering challenge of our era, honestly. And frankly, my position is that pure physics just cannot be ignored. Immense mass fundamentally compromises true mechanical handling. And supplying up to, 1,000 horsepower to push that heavy chassis around a circuit, it is going to absolutely destroy track longevity.
I hear you. But my position is that the rules of the game have fundamentally changed here. I would argue that the ZA0's new quad-motor architecture and track-optimized battery chemistry effectively rewrite the rules of physics, making this M3 more agile and track-capable than any of its combustion predecessors.
I mean, that is an incredibly bold claim for a vehicle carrying a 100 kilowatt-hour penalty in the floor pan.
Let's break down exactly how this agility is achieved, though. This isn't just a heavy car with a big motor. Yes, it is built on the Gen 6 New Class platform.
Which is what, 10% lighter?
10% lighter than Gen 5, yeah. But the real magic is the quad motor setup. We are talking about 4 independent motors, one per wheel.
Right. Replacing mechanical differentials entirely.
Exactly. And let's look at why that matters. Unlike a mechanical diff that just breaks the inner wheel and, loses momentum to turn a car, a quad motor setup actively overdrives the outside wheel,
while regenerating power on the inside wheel.
Right. It effectively pivots a heavy car on its axis like a tank, creating this unnatural, hyper-responsive turn-in. Think of it like a modern fly-by-wire fighter jet. Those jets are aerodynamically unstable by design. They shouldn't be able to fly. But software micro-adjustments generate extreme agility that the raw physical shape wouldn't normally allow.
I'm sorry, but I just don't buy that. Let me tell you why. I have a really hard time with the fighter jet analogy. Jets are fighting air, which is a fluid. A car is fighting solid asphalt through 4 tiny contact patches of rubber.
Well, sure, the medium is different.
It is totally different. Masking weight with software torque vectoring isn't the same as true mechanical agility. When you have a battery that large, you are carrying massive momentum into every single corner. Your software can spin the outside wheel perfectly, but the tires and the brakes still have to physically manage that immense kinetic energy. You simply cannot code away inertia.
You can't code it away, no, but you can manipulate it faster than mechanical parts ever could. The control algorithms adjust torque to each individual wheel in milliseconds. The software is dictating exactly where the weight transfers before the chassis even has time to roll.
Dictating where it transfers, yes. But you can use software to dictate weight transfer all you want, and physics will still collect its toll. All that friction and kinetic energy generates immense heat and energy draw.
That is a fair point about the heat.
Right? Because if your software and your tires are working overtime to force a heavy battery pack through hairpin turns, you are forcing the battery to do the heavy lifting. High-performance EVs have a notorious track record here. Supplying 800 to 1,000 horsepower across 4 motors means you will chew through a 100 kilowatt-hour pack remarkably fast. It severely limits your actual track day sessions.
I see why you think that, but let me give you a different perspective. I completely get the range anxiety, especially on a track. But look at the actual cell chemistry BMW is bringing to the table here. They aren't using off-the-shelf cells.
They are using the newer cylindrical ones, right?
Yes, they are utilizing designed-to-power 46 by 95 millimeter cylindrical NMC cells. Let me explain why that matters. By using a wider 46 millimeter cell, they are significantly lowering the internal electrical resistance. That means the battery doesn't waste energy generating massive amounts of heat when you floor it.
So it stays cooler under load.
Exactly. It stays cooler, allowing for sustained high output on the track instead of instantly overheating. Plus, resting the front motors on straights preserves even more thermal capacity.
Lower internal resistance helps manage battery heat. Absolutely. But sustained high output still generates an immense thermal load on the rest of the car, especially on the brakes trying to stop that heavy chassis from 150 miles per hour.
Which is where the regenerative braking of the quad motors takes the strain off the mechanical brakes. And when you do finally drain the battery, well, because it runs on an 800-volt architecture, it can suck in over 400 kilowatts of power during a pit stop. So even if the weight drains the battery faster, you are getting back on the track in 15 to 20 minutes. That is exactly the length of a typical track day brake.
Well, that assumes the track actually has a functioning 400 kilowatt charger, which is a massive infrastructural hurdle right now. But focusing purely on the vehicle, relying on 15-minute ultra-fast charging as the ultimate solution to EV weight feels like a workaround for a car that simply shouldn't weigh that much to begin with.
We are looking at a profound paradigm shift here. I see sophisticated code and ultra-fast charging as the ultimate tools that conquer EV weight limitations, while you see inherent mass and rapid energy drain as unconquered hurdles for a pure driver's car.
Exactly. Though I will concede, regardless of the cornering physics or the thermal loads, the straight line performance is going to be completely unprecedented. Hitting 0 to 60 in the 2-second range with instant four-wheel electric torque is undeniably impressive.
It is staggering. And exploring these opposing perspectives is so crucial to understanding where high-performance engineering goes from here. There is much more to uncover in how these systems will interact on real asphalt. We don't have all the answers yet, but it forces us to ask a fascinating question. If we build a remarkably heavy machine that relies entirely on software to make it dance, are we still driving the car, or is the fly-by-wire jet flying us?